It is my pleasure to introduce Annie Kritcher. She got her PhD here in 1909. Whoops, 2009 is while here. Anyway, she is the first person on the planet to achieve thermonuclear ignition in a laboratory. That counts for a hell of a lot. And so she's going to tell you about her experiences, along with 1,500 supporting staff, the little people you have to thank you. Right? But anyway, she got her PhD in 2009 from here, and also a master's here, and was at the University of Michigan as an undergrad. Is that right?
That's right.
Yeah. And so anyway, just another side note, in addition to her other accomplishments, she's married to Ging Wu, another one of my former students. I only signed on the second line for him. And they have 3 children. So I'll let her take it over, but I hope that she's a role model for prospective students and current graduate students. Thank you very much.
Thank you, Ed, and I hope my voice doesn't cut out during the talk. I'm getting over a cold, so sorry if that happens. Today I'll be talking about achieving target gain greater than 1 in fusion experiments at the National Ignition Facility. And as Ed said, we had quite a few people working on this, so I'd like to thank the larger ICF team and some of the people here in this audience as well. So on December 5th, 2022, this marked a significant advance in ICF research. We achieved something that showed that there's nothing fundamentally limiting achieving fusion gain greater than 1 in a laboratory, controlled laboratory experiment. And I'll talk a little bit more about this, but when we say gain 1, we mean we got more fusion energy out than laser energy required to drive the target. And you can see that here in a plot of neutron yield in megajoules as a function of calendar year. You can't quite see it, but this is when we first started out doing shots in the National Ignition Campaign. There are little bars here, and this is the most recent experiment where it's about 1.5 times the energy that was imparted to the target. I'm going to walk through this entire history, so bear with me a bit. Sometimes people fall asleep during that part, but I hope I'll keep it exciting. We learned in steps, and so even though we started out low here, each thing that we did enabled us to make the next step. And once you start eliminating issues that you have in your system, then things really start to begin to take off. So this experiment reached over 30 quadrillion watts for 90 trillionths of a second. Pressure is greater than 2 times the center of the sun, and temperature is greater than 5 times the center of the sun. It now meets all the definitions for ignition. So previously we had an experiment here which met the scientific definition for ignition. Now we've also met the National Academy of Sciences definition of ignition for the National Ignition Facility. So we can finally say we put the I in NIF. So there's been quite a bit of work on this, starting in 1972 with the Nuckolls paper, which first proposed thermonuclear microfusion explosions with lasers. And then the ICF program was born out of this as a byproduct of the Cold War. It was realized that you could make these little microfusion explosions with high enough energy density to get to the conditions where we can also support the stockpile stewardship program. And so in the beginning, we didn't know exactly what it would take. And so the first lasers were the joule level, then 10 joules, and we had a 500 joule laser, then a kilojoule laser, and then NOVA, the 300 kilojoule laser. That still wasn't quite enough to get to the energy densities we needed to get to ignition. So then that brings us to the National Ignition Facility. We're finally there now. It's a 2 megajoule laser, and that's what it took. So experiments performed at the National Ignition Facility. It's the world's largest, most energetic laser, finally enabled the creation and study of these microfusion explosions in the laboratory. This laser is the size of 3 football fields. It's 192 laser beam lines. There's quite a bit of infrastructure here. All the lasers come and are focused into the center of a 10-meter diameter target chamber shown here. And there's a little picture of that here as well. Inside of that 10-meter diameter target chamber sits a 1 centimeter long target, this little, what we call the hohlraum. All the laser energy is focused into this hohlraum. And then inside of the hohlraum sits a tiny BB-sized capsule that contains the fusion fuel or the deuterium-tritium fuel that's shown here. And then we squeeze and compress that capsule down to the size of half of a human hair. So all of this is needed to get ultimately to the energy densities we need in a plasma that's half the size of a human hair to make ignition, reach these conditions. So to reach fusion ignition and also gain in ICF experiments, so more fusion energy out than what we put on the target, this requires heating and compressing of deuterium-tritium fuel to very extreme conditions and also for a duration of time. So a Lawson-like criterion. Fusion reaction over here, we have deuterium and tritium that fuse together that produces an energetic neutron and alpha particle. This reaction is very difficult to achieve because you have to overcome the electrostatic repulsion between the deuterium and tritium. And so this is why we need these extreme conditions of tens of millions of degrees. And as you can imagine, it's difficult to get a large amount of fuel to those conditions. So what we're doing here in this approach at the NIT is what we call hotspot ignition, where we only try to get a small fraction of the initial fuel to those conditions in a central hotspot. So here's a time equals 0 pie chart of the capsule that contains the fusion fuel. The capsule is depicted by the sort of tannish color there. That's made out of diamond, plastic, or beryllium. And these experiments made out of high density carbon, which is diamond, but not single crystalline, unfortunately. And then inside here, we have our frozen deuterium-tritium ice layer. And then inside is filled with DT gas, deuterium-tritium gas. And so what we try to do is we try to heat and compress the initial DT gas and a very small fraction of the DT ice to these conditions. And the way we do that is by doing mechanical work on that material using a piston that is also made up of DT fuel. So what we have here is we implode the fuel, we heat and compress a central part of the initial fuel using a piston that does mechanical work by imparting the high kinetic energies and that's converted to internal energy. And that piston is also made out of fuel. So that's really important. This is a depiction of what's happening at peak compression or when the implosion has squeezed down to the smallest volume that we're going to squeeze it to. We have a central hotspot here in the middle, and that's our DT fuel piston surrounding it that's not quite as hot, cooler, denser fuel surrounding that. So the idea here is that we not only want to get to these extreme temperatures, but we need the pressures so that we can reabsorb the alpha particles that are born in these reactions to also heat the plasma. That's a self-heating. So without being able to trap the alpha particles or reabsorb the alpha particles, we would never be able to reach the conditions for ignition just by doing mechanical work on the hotspot. It's just too hard. So we have to retrap these alpha particles. And then if you can get to the right conditions, then you get ignition, and it's sort of a runaway bootstrapping process where then you've ignited the central plasma and it sends a burn wave out through the remaining cooler, denser DT field, trying to burn up more of the fuel. So the issue here is that we're working against time. There's losses in the system. We have the plasma is trying to radiate its energy away through Bremsstrahlung. The plasma is conducting energy away. And then another big mechanism of energy loss here is that the implosion, once it gets really extremely hot and high pressure, it tries to explode back out. And of course, as soon as you start exploding the implosion back out, it cools very rapidly. So it's a race against time. We're trying to implode it to the right conditions, burn up as much fuel as we can before the thing disassembles and it falls over. So another very important aspect of the fuel piston that does work on the hotspot is that it also provides a way to tamp the implosion to hold it together longer for longer confinement times and more burnup of the fuel. So at the NIF, we use laser indirect drive to create the X-rays to drive the implosion. So this is walking through that process here. As I mentioned, the laser beams come into the hohlraum, what we call the hohlraum, which is a cylindrical hollow can made up of a high-Z material, such as, in this case, a gold line depleted uranium hohlraum. And so when the lasers hit here, they create an intense X-ray radiation back. This is the capsule that's sitting in the center of the hohlraum that contains the fusion fuel. You'll note it's supported in the center of the hohlraum with a very thin tent. I'll show that in a couple of slides. It's very impressive what target fab can do. And so that creates an intense X-ray radiation back of about 3 million degrees. And then what that does is that heats the outside of the capsule that holds the fuel, that explodes that material. And in a rocket-like effect, that explosion sends the remaining ablator material and fuel inward, and that's what lets us squeeze and compress the plasma. So then the idea is if you can reach the conditions for ignition, you get up to about 500 billion atmospheres in that little hair-sized plasma. And then if you can, if the implosion is good enough, you can hold it together long enough, you can burn through the remainder of the DT fuel. But achieving the conditions for ignition in the first place and also burning up of the fuel demands precise control of the design, the laser, and the target parameters, and all at the same time. So the targets that we shoot are engineering marvels. There's been decades of R&D that went into making this possible. This is a picture of one of our hohlraums here, and these are cryogenic cooling arms. This is the capsule sitting in the center of the hohlraum. This is a very thin tent, what we call the capsule tent, that holds the capsule in the center of the hohlraum. That's tens of nanometers thick, and it's so impressive. And the reason it has to be that thick is because that can see hydrodynamic instabilities, and so it's a very important aspect and delicate aspect. This picture over here is a radiograph looking down the laser entrance hole at the target. This is our diamond, and we have it doped here. I may or may not talk a little bit more about that later, depending on the time. This is the DT ice layer, the DT gas core. You'll notice down here, I don't know if you guys can see it or not. I can barely see it. I'm standing right next to the screen is our DT fill tube. So there's a tiny little 2-micron size fill tube, a hole that goes in here, and that's how we get the fusion of the DT fuel into the capsule. We also worry about that seating instabilities, which is why it's so small. So this is quite impressive. This is a picture of before. So this is the hohlraum here at the end of the cryogenic cooling arm assembly. And this is after the experiments of this entire part of the target has been completely vaporized. So many design parameters need to be considered simultaneously to achieve these conditions. I apologize if some of this might be information dump, but I wanted to kind of touch on some of the things that we care about when we're designing the implosions. So here we have to maintain a low adiabat of the fuel that's coming in. So we want to keep the dense DT fuel piston nice and dense to do the most efficient work on the hot spot, and that lets us on a low adiabat better compress the DT fuel piston. And so it's also important for the confinement time as well. We also want to achieve high implosion velocities. So we want to implode the capsule as fast as we can, also considering some of the instabilities. And we also want to keep a high late time ablation pressure. So the lasers are creating this intense X-ray oven, and we want to keep that on long enough in the implosion history so that the shell doesn't decompress before it's reached its minimum volume. And we also care about managing hydrodynamic stability. So hydrodynamic instabilities can send the capsule or ablator material, send chunks of it or sheets of it into your hot plasma. And that this is fire Z, and that causes the plasma to radiate energy away very quickly. And that can very quickly result in a dove-like implosion. So that hydrodynamic stability is a product of both the design stability, so you can design your implosion to try to be more stable, but also the seeds for the instabilities, such as the capsule support tent I mentioned, the DT fill tube, how smooth all of the surfaces are. If our surfaces are a little bit rough, that can seed instabilities. And then finally, we worry about low mode asymmetries. So here you can see something that doesn't look very spherical. This is the dense fuel surrounding the hotspot. That's a picture of that. Also, the hotspot isn't very spherical in that picture. And what that does is that doesn't allow you to have an efficient piston to do the most work on your hotspot. And also you can get thin spots here in the shell, which lead to loss of confinement. One other thing to point out here is that what's best for the implosion to optimize all of these things together is typically work for what we can do with the lasers in the hohlraum, unfortunately. So that's one of our biggest challenges. So the way that we design these experiments is using a variety of tools. We have radiation hydrodynamic simulations. We also have analytical theories, which help us guide our thinking. And we have our semi-analytical models that are benchmarked against experimental data. So what I'm showing on this slide are examples of the radiation hydrodynamic simulations, and those are also heavily benchmarked against experimental data. So we do this design process in a two-step process. First, we model how the lasers enter the hohlraum and create the radiation drive together with the capsule. That's benchmarked. I'm not going to go through all of this right now, but various pieces of data that's taken in focus experiments to make sure that we're getting this right. And then we take the radiation drive from here and apply it to high resolution capsules where we only model the capsule by itself to try to resolve some things like these roughness, perturbations from the roughness and the tent and the filter. So I'm going to walk through the pieces of the laser pulse and what they mean for designing. So here's an example scaled laser pulse. And when I say laser pulse, I mean the laser powers we define at very specific times. We don't just blast the target with all the laser energy at once. And that's really important for designing the implosion. So here we have a scaled down laser power, which has a step, a trough, a step, a peak, a main peak. And I'll go through what each part is important for. So here we have this first peak, second peak, and rise. They launch discrete shocks into our ablator and DT. And what that does is that's important for sighting the adiabat. So making sure that we can more efficiently compress a DT fuel by coalescing multiple shocks. So if you can shock something that's already been pre-shocked, it can be compressed on a lower adiabat or lower entropy. And this here is an example. This is a pie chart of the capsule. And this is a gradient of the pressure of the shocks coming into the capsule and the fuel. So this is the capsule here, and this is the fuel here. This shock launches this first shock coming in, this first power step. Then we have a second power step coming in here, and the third power step coming in here. Then we start, once the shocks coalesce and break out of the DT ice layer, then the shell starts to accelerate. So then we accelerate the shell to about 400 kilometers per second, so extreme velocities to do work on the hotspot. And we reach peak implosion velocity at a convergence of about 6. So we convert it down there. This peak of the laser pulse is very important for setting that implosion velocity. And we also rely on our models and also our data at these very extreme implosion velocities to be able to also manage the instability growth at the interfaces, which is something we worry about in these implosions. So this is an example here of the interface between the capsule material and the DT fuel. And you can get Rayleigh-Taylor mixing at that interface. And so a lot of the design considerations have to take that into account as well. So we try to maintain a good Atwood number so we don't have a light material pushing on a heavy material. We try to also keep up the density of the ablator materials to minimize these Rayleigh-Taylor instabilities. And then we get to our peak compression. So here now we've converged down by about a factor of 25, 25 to 30, depending. And the late part of this pulse here and how long this stays up here is very important in this phase as well, so that you can couple the most energy to the hotspot and also doesn't decompress. So now I'm going to walk through starting from the beginning of the NIC and how we've made improvements based on understanding. So we do experiments, we figure out what's wrong through our diagnostics, and then we try to make improvements. And the best way to kind of show the improvements that we've made at NIC throughout the last decade and more is by looking at a plot of hotspot pressure versus hotspot energy. So as I mentioned, we're trying to get to extreme temperatures in the hotspot and extreme pressures. So we really need high energy densities to get to ignition. So in this plot, we also have the theoretical ignition boundary here. And the gray points are simulations. That's not data. I was going to ask that question. So the idea here is if you can get enough hotspot pressure and energy, you'll cross the ignition boundary, and then you'll have propagating burn into the remaining DT fuel. This plot takes out the impact of alpha heating on these quantities because otherwise everything's amplified. It's hard to see how close you are to the boundary. But one thing you can note here from this plot is you can get extreme pressures, but if you don't couple enough energy to the hot plasma, it won't work. And you can couple a lot of energy to the hot plasma, but if you can't squeeze it to the high pressures, it won't work. Cross ignition boundary. Okay, so here's in the first part of the NIC, I'm going to accelerate through, most of it in the interest of time here. There's 3 distinct regions. Those were different design eras to try to fix issues that we saw in our implosions. So these platforms, starting at the beginning of NIC, made improvements in the stability and the symmetry mainly. So starting here with a low foot design, the first design that was fielded on the NIC, it was a very high gain design, and it was designed to be on a very low adiabat. It wasn't very stable. So all these wiggles here you see in the capsule are resulting from hydrodynamic instabilities. And then in addition, so sorry, I didn't mention this before, this is the dense DT fuel, simulation of the dense DT fuel surrounding the hot spot here. And in addition to these wiggles here, you can also see the feature at 45 degrees, that's the tent perturbation. So the tent that holds the capsule was jutting material into the implosion. And this here is from the fill tube that was jutting material into the implosion as well. Another thing to point out is this looks very non-spherical. It looks very diamond-like and elongated. So early on, we had a lot of trouble with the hohlraums and laser plasma instabilities. So the laser comes in and interacts in a way we don't like with the plasma that's being filled in the hohlraum, and that scattered light back out. It also made the symmetry very hard to control. So then moving up here, we increased the pressure of the hotspot by reducing these instabilities at the high foot, and that was by making a laser pulse change. So we put it on a higher adiabat, and it wasn't as susceptible to the instabilities at the ablation front. But it still had this issue of the symmetry and also the tent perturbation feature. These were both plastic capsule implosions. And then another big advance was moving to diamond ablators. So these diamond ablators, because of their higher density, weren't as susceptible to the capsule support type feature. And another key feature of diamond is because of its higher density, you can have the same mass in a thinner layer, so you can better control the symmetry because now the laser pulse doesn't have to be as long to get the shocks where you want them to go in a thinner layer. And as you can see here, we're able to better control the symmetry. It looks more spherical than it did before. But the issue here was that these starting, now let us push up the hotspot pressure here. So the issue though is at this time, these designs were maxed out in laser powered energy. They were using the maximum NIC. And so the only way to get more energy coupled to the hotspot at that point was to increase the size of the implosion. So we needed a bigger capsule, but we couldn't just scale up the whole system because we didn't have any more driver energy to do that. So being able to increase the scale of the implosion to move right on the spot, but not let the pressure that we achieved drop was a major challenge, and is something that we've been working through to cross the ignition boundary. So as I mentioned, what's good for the hohlraum is usually worse for the implosion. So when we increase the scale of the implosion, we knew that we'd have to sort of re-optimize all these other parameters. so that we could go right on the spot, but not let the pressure drop too much. We also knew that it would be hard to balance it if we went too big at once, so we set out to try do 2 different implosion scales. I don't have time to talk about all the trade-offs, but I wanted to talk about one of the big and obvious trade-offs here is that when you increase the scale of the implosion, but you don't have more driver energy to just scale up the whole system, you have to make the hohlraum more efficient, and that becomes harder for the low mode symmetry, or the symmetry of the radiation drive that can cause these low mode asymmetries. Excuse me. So here is an example, this is in John scale, of the previous configuration versus the first attempt at scaling up the implosion. And what we did was we squeezed a much bigger capsule into almost the same size of hohlraum. So even though we have more laser energy now, we have a more efficient hohlraum so that we can drive these larger scale implosions. That becomes more difficult for achieving a nice uniform radiation drive around the capsule, which is important because it's depicted by the cartoon shown here, as well as the radiation hydrodynamic simulations on the left-hand side. So these simulations show the material boundary, and the gold region here is where the wall is blowing in from the lasers hitting the wall. It blows in, so you're trying to get the laser beams in while the wall is blowing in. And you want to get the laser beams to go exactly where you want them to get a nice uniform radiation drive. And we have to do this for the entire pulse duration. Here's a cartoon of what's going on. So one of the biggest challenges here is that our beams that hit the outside of the hohlraum blow in the plasma into the path of the beams that try to get to the center of the hohlraum. And also we have the expanding of later. So for the bigger capsules where you don't have as much space to get the inner beams past this bubble, and you also have to keep the laser pulse on longer, this becomes more difficult. So a couple of the key advances in this new era was to, first of all, use our data-driven models to guide the hohlraum design choices. Because it's very difficult, this piece here is very difficult to calculate. So to get that correct faster, we used our data-driven models. And then in addition, we used cross-beam energy transfer to move energy from the outer beam, from these beams, give it to these beams so that you don't have too low of radiation drive at the center of the hohlraum. What that does is that makes a pancake implosion. This has been done since the beginning of NIC, and then we moved away from it because of the laser plasma instabilities that I mentioned. But a key difference here is now applying this cross-beam energy transfer, so giving energy from one laser beam to another. We did that in a different hohlraum configuration where we didn't have these laser plasma instabilities. So the initial test of increasing the scale to move right on this plot did work. We moved quite a bit over. We coupled a lot more energy to the hotspot. But as you can see here, I'm looking at this region here, the pressure dropped. And that was for a couple of main reasons. One is that what we call the coast time got worse. So as I mentioned, you try to keep the radiation drive on as long as you can before the thing compresses to its smallest volume. And if you don't do that, it doesn't couple the most energy to the plasma, and it can lead to decompression. And there's a plot of that shown here where we have our radiation drive. We have our laser pulse and the radiation drive that comes with it, capsule radius here, and it's reaching its minimum radius. And you want to keep this drive up long compared to when it reaches its minimum radius. The larger capsules take longer to implode and reach minimum radius. And if you only have a fixed laser capability, you only have a fixed laser energy driver, that's harder for the larger scale implosion. So that was the 1100 that we tested here. And in addition to that, we also, in the first attempts to scale up the implosion, it was very difficult to make high quality diamond ablators. They had a lot of voids or the holes inside of the diamond ablator, and that seeded hydrodynamic instabilities. And so what we did to get up here, where we went back and increased the pressure again of the hotspot. We gave up a little bit in hotspot coupled energy, that increase the hotspot pressure by making the plasma by making the capsule, the initial capsule, only 50 microns smaller in radius. So again, about the size of a human hair, by just making it that much smaller, we could still couple more energy, but regain the pressure. And that led to the burning plasma results from a couple of years ago. So simulations suggested that we were still not optimized in this coast time, and we wanted more drive, but we didn't have more laser energy. We also didn't want to give up the energy that we coupled, so we didn't want to go back to a smaller scale. So in the next step, what we did was we had an entire dedicated effort to make the hohlraum even more efficient. And that is basically reducing the openings at the ends of the hohlraum where the lasers enter into the hohlraum. We made those smaller. That's one of the main sources where radiation is lost. And so if you can make those smaller, you make the hohlraum more efficient, so you can get more drive out for less laser energy, which is what we want here. But this is a little picture here of a laser beam coming in. If you just squeeze the holes down, but you don't move the lasers around, then they won't get into the hohlraum, of course. And so you have to move the lasers around, but then when you do that, it screws up the entire radiation drive symmetry and your beams don't go where you want them to. So that all had to be reoptimized. And when we did that, we did observe both an increase in hotspot pressure from the reduced coast time, as well as coupling more energy with the efficient hohlraum led us to this experiment here, which was August 2021, the first scientific demonstration of ignition, crossing the ignition boundary. One more thing to point before I leave this slide is the more efficient hohlraum let us reach the same radiation temperature with less laser power, and that gave us more energy that we could tack that onto the end of the pulse, and that's how we reduce the coast time. So we've been looking a lot at this plot where the impact of alpha heating is taken out of these quantities, just to see how close we are to the boundary. When you, in reality, the real pressures and energies are amplified by alpha heating. And what that does is that leads to a rapid increase in fusion energy output. And that's this point shown here. So relatively small changes in this space compared to the changes that were made before, once you get closer to the ignition boundary, are amplified by the alpha self-heating from the hotspot plasma. So I'm not sure how many people are aware of the variability experiments that happened just following that first demonstration in 2021. We had a few experiments where we tried to field the same shot again. Those experiments reached about 50% of the yield maximum. And that was due to two specific reasons. So it's great that we have all these amazing diagnostics at the NIF so that when something doesn't go right, we can figure out what's happening and try to fix it for the next time. So the two main degradation mechanisms versus 210808 is that the quality of the diamond was reduced. And so we had more seeds for hydrodynamic instabilities. We actually observed this in the X-ray images. So we imaged the hotspot with our X-ray diagnostics. And we see these bright glowing features here. These are we call them meteors. It's when the high Z ablator material gets sent in and glows and radiates energy away. And so we actually directly correlated that to like one of the capsules had a big flake, a high Z flake on it. Unfortunately, it caused this feature here, and that prohibited us from getting to ignition on that experiment. Another thing that happened, and sort of these happened on different shots, so we did really get unlucky. Another thing that happened was unintentional odd mode asymmetry. So I talked a lot about how pancaked it was and how we try to design things around to get enough energy to the inside of the hohlraum so we can make it spherical. There's also the case that happens when the laser can fire differently top to bottom. That's not a design thing, that's not intentional. That can cause an odd mode asymmetry that looks like this. This is a hotspot simulation and the shell that surrounds it, where essentially you're squirting your hotspot out in one direction, and that doesn't efficiently couple energy to the hotspot plasma. So that also can preclude you from getting to ignition. So then the next two experiments, which led to the fusion gain result, are part of a new effort to try to make our lives easier, so that we didn't have to always feel the most perfect capsule, and we didn't have to worry about laser variations. And we call it the higher energy, thicker ablator campaign. So the higher energy, thicker ablator campaign was enabled because the laser team did an awesome job of squeezing a little bit more juice out of the driver. The laser went from 1.9 megajoules on target to 2.05, which doesn't sound like a big change, but it was really important. So this is the laser pulse shown here. The black is the original one from the previous design, and the red is the one from the little bit extra energy design. To start out with, we were allowed to get a little bit more energy, but tacking that onto the end of the pulse at the same power. And what that does is that raised the late time ablation pressure even more. The estimates going into this was, okay, we could reduce the coast time even more, and that's great, it worked before. But a better use of this extra energy at this point for this implosion was not just to try to reduce the coast time even more, that would have been like a 40% increase in yield. It's to try to couple more of that extra energy at the end and drive a thicker ablator. So make the diamond thicker and make the implosion, the ablator thicker coming in. So, another thing to note here is I won't spend too much time on this because I already talked about this exhaustively. When you make the pulse length longer, there's more time for the hohlraum to plasma fill. And so you have to re-symmetrize the whole radiation pulse. So that had to happen as well. So driving thicker ablator implosions versus just reducing the coast time, we expected to be able to increase our margin on this plot that we've been looking at quite a bit. And that's this dark arrow shown here. So the idea was, could we get further over the ignition boundary so that when we have things like imperfect targets or laser variations, it pulls us back, but we still can get ignition or megajoule yields. And then if everything goes right, we can get more fuel burnout because we're now into this burn regime. See if I can make it to the end of the talk here without losing my voice completely. The thicker ablators are good for a variety of reasons. They increase the confinement time, so higher burnout fractions. They allowed us to, the implosion stayed larger, longer, so we absorbed more of the radiation drive. And that's how we got this extra margin here in hotspot pressure and energy. And another big aspect is the stability at the interface between the capsule and the fuel that I talked about earlier. If you have more ablator and it's compressed more to higher density and at the same or higher density than the fuel that's right next to it, you have less Rayleigh-Taylor mixing at that interface. And so that helped us have a more clean fuel fraction on the outside of the DT field, which is important for burning more of the fuel. We actually observed this in one of our diagnostic analysis as well, which is kind of cool. This is a different way to visualize what the intent was of going into this new campaign. So with the extra margin in the pressure and energy and also the confinement, the idea was that we could tolerate more perturbations and still reach high yields. So this is a plot here of yield, fusion yield versus increased roughness at all of the interface. And what that means is I'm essentially dialing up in the simulations a perturbation mechanism. The one I'm dialing up going to the right is shown over here. This is the hot spot and the dense shell. I'm increasing the speeds for the Rayleigh-Taylor mixing, so you get more fingers and you have more mixing between the ablator and the ice layer, and also more fingers that poke into the hot spot. So as you go to the right on this curve, as you go right on this plot, you can see this is the previous design in black. It has a certain sensitivity to this perturbation. And then this is the new design. So if all goes well, we get higher yields. but in the presence of a perturbation, you can tolerate more perturbation and still reach the same ignition conditions. So the first attempt was in September, and actually we unintentionally proved what we had wanted to going into this, was that we did have a perturbation unintentionally, but it showed that even with a perturbation, we still reached these over a megajoule yield. And this shot actually did also satisfy the Lawson criterion for ignition. So in that first attempt, we didn't have a lot of tuning shots are hard to do at full power and energy to this degree. So the first attempt to make the implosion more symmetric and re-optimize the symmetry ended up with something that was close but too squashed. That impacted the performance, and that's similar to the odd mode asymmetry. It does a similar thing to the hotspot. That was an issue for the variability test. So we already know when we have a similar type of perturbation as we did before here, we can still reach high yields. Another thing is that the capsule, so the thicker capsule that we had ready to go for this experiment, had all these like hundreds of higher Z inclusions inside of the HTC capsule. We're still not 100% sure what that did to the implosion. And that we're planning to test that, so we have good capsules without these inclusions that we're going to test at the end of April. So because in a post-shot sense, so we look at these things post-shot too and try to make sense out of them. The post-shot simulations indicated that a lot of the yield reduction for this experiment versus its full potential was due to this asymmetry that motivated a test to retune the symmetry. And so what we did was we gave a little bit more energy from the outers to the inners. And then this is a plot here showing how the laser powers are defined differently for the different sets of beams. So the beams that hit out here follow this orange profile, and the beams in blue here follow this profile in the center, this profile here. And so they're balanced very differently to try to get this time-dependent radiation symmetry, radiation drive symmetry. And so in addition to giving more energy from the outers to inners, we also made these adjustments here between the dashed and the solid lines, which look very tiny, but actually are very important for the implosion. And just that change gave us a more symmetric, more spherical looking implosion and increased the yield by more than 2.5 times. That's what led to the December 5th, 2022 experiment. So, and everyone's going to ask about IFE. NIF is a basic research facility. It's not designed to be plugged into the grid, but it's a facility where we can study these plasmas with the best diagnostics on the planet. And it's a really exciting time. There's a lot of other companies that are looking into fusion energy concepts, and also research institutions like the lab that are also looking at this. But the important thing about this shot is it's a proof of concept for fusion gain over energy used to drive the target. But of course, there's a very long way to go. The lasers that we use at NIF aren't efficient. The scheme of coupling energy to X-rays to then ablating the implosion isn't efficient. So credible fusion schemes would need higher gain designs also, engineering developments, cheaper targets, and more efficient lasers. And people always want to know what's next. So we continue to study the parameter space. So one nice thing is now that we have these igniting plasmas, we can intentionally perturb them and see if our predictive capability is in line with what we observe. And we also, of course, want to push to even higher yields. And we've also started to use this for applications for the stockpile stewardship program. So here we have already begun some of this variability of the new system and robustness. We, on this December 5th experiment, actually fielded a stockpile stewardship application diagnostic, which is really cool. So I was always nervous about making a change on a shot where you have a customer, so luckily it worked. And then, excuse me, to push to even higher yields, we have kind of two-pronged approach. One is trying to increase the compressibility of the DT fuel piston, which is really hard to do. So if there's ways to get back to the lower adiabat designs with better stability, and then also trying to drive even thicker ablators as we get more driver energy and more efficient hohlraums. So we're also trying to continue to couple more energy to the hot plasma with more efficient hohlraums, and also more laser energies coming online in the next few years. So with that, I will take questions.
I commented on the efficiency of the hohlraum, and a lot of that comes in from the laser coupling and X-ray energy. Can you comment on like the quantitative value of that efficiency and how that evolves during the course of your laser pulse?
Yeah, so let's check my spot. So this, let's see, where's my cursor? This is depicting the amount of laser energy into the hohlraum. And then this is the amount that goes into the X-rays. We also have some scattered light back out of the hohlraum. We also generate hot electrons in the process of making the X-ray driver. We also, some of it goes into the low density plasma, and then we lose some through the LEH, and we lose a lot through heating of the hohlraum walls. So then in the end, only a little tiny bit here, a small fraction, about 10 to 20% of the initial laser energies is imparted to the outside of the capsule, and then even less of that gets to the hot spot. And so in the course of what we're trying to do, we're trying to take a couple more of what's absorbed by the capsule to the hot spot by making it more symmetric and reducing the mixing. But we're also trying to improve the efficiency of the laser driver to coupling energy to the capsule. One of the ways we're doing that is by reducing the area of the hohlraum walls so that we have less wall loss at wall heating. That's a frustrum. You may have heard of it. It sort of looks like this. I need to put a picture out of this talk. People always ask. So it essentially takes this part of the hohlraum and chops it off, which is less wall area. And we think we can get 14% more efficient. And that the challenge there is controlling the symmetry again. So that's what we're working through right now.
Two technical questions. One of them was the high C inclusions that you alluded to. What were they? How many atoms are we talking about?
Yeah, let's see if I have this slide on that. I think we're always trying to figure out what these are because we always get new features as well. Silicon carbide, I think, and yeah, I don't have a picture of the total volume of that. I don't know if it's not
Could you find out like how many atoms? Because that would be really didn't ruin the party.
Let's see here. Let me go back to the picture that shows it. So okay, you can kind of see here. So this region is the doped layer region, which is about 18 microns thick.
Right.
And these inclusions are quite large, so they're 10 microns. Right? They're like all these like little flecks here are almost the width of the doped region, and they go throughout the entire region. And so the question is like, are we robust enough that the implosion went there? Because once you ignite, and you just got burning that, so maybe it doesn't matter. But it also probably does something to the compressibility of the fuel surrounding the hotspot. And we have some time dependence in a way that it's just like impossible to calculate this. So we can do like one of them. We can't do multiple at crosstalk. So so we do have really pristine capsules that actually the Livermore team worked really hard with diamond materials to make. We don't have any of these. We almost shot one last weekend with the targets fell off the field too, unfortunately. It happens. It's so frustrating. Wait months.
I wanted a quick technical follow-up. Aerial density, the shot that actually created ignition, what was your row R?
The hospital like 0.4 or something.
It's 1.4.
Yeah, and then the total's like.
What was the DSR look like for the neutron?
So from the gain shot, they haven't given us even like a performance compensated one. So we have the primary neutron image, which I showed. That's what I was showing. We have the downscattered neutron image, and there's a way to try to take the primary image and account for the fact that it's an extended source size. Because you want to see from the downscattered neutron image how many of those primary neutrons scatter in the fuel, and that gives you a picture of how uniform your fuel is. I don't know if I have a picture of an example. It's really cool. It's called Fluence compensated downscattered neutron image. Aha, I do. Let's see. Let's see. Right there. So that's an example of one, like, have a different shot where you can clearly see there's blobs on the top. You have these what we call polar caps. The fuel's thick on top and thin on the side. We don't have that yet from the thunderfish shot, and I think it's just really hard for them to analyze that. I'm not sure if we'll ever get it. Yeah, but all the diagnostics are they need development and different ways of analyzing. They either need development to work in these higher versions or to analyze the data. But we do have an intentionally dotted experiment we're going to do in the same exact configuration. So we change the amount of the ratio of D and T and add an H, so THD. And then we get the same implosion, but without the yield. And so there we'll get a nice neat picture of the fuel response of it.
I have a question, and you know what I'm gonna ask, and that is this LPI issue with these design changes. Has anyone handed you a knob now so that you know, and what, I presume you've been measuring LPI in
Yeah.
shots and what's happening and how do you control it?
Yeah, let me go back to plot. Okay, so this is how I spent the first 5 years of my life. At NIP was trying to control the symmetry when we have these LPI issues. So in the first designs at the NIP, we had a really small hohlraum, smaller than that by quite a bit. And the way that the design originally was to hold the wall back with a large amount of helium filling this hohlraum, helium gas fill. And when we tried to do cross-beam energy transfer, we tried to move transfer or energy from one beam to another beam in the presence of the high gas fill, had a lot of issues with scattering light back out of the hohlraum, and it reduced efficiency about 10 to 30% of the hohlraum. And so in addition to that, we weren't really sensitive to as much as we are now, because a lot of the energy we tried to transfer to the inner beams just went into electron plasma waves, and some of the issue that was stimulated Raman scattering out and stimulated Raman scattering out of the hohlraum. So then we went to an era where we moved away from this, and this was like, it was impossible to model. It would change shot to shot, or any design change, it would change. And so controlling the symmetry specifically in the early part versus the end of the pulse was like near impossible. And if you don't get the first part of the symmetry right and just the end, then you set up these, we call them symmetry swings. You swing the symmetry, and that can create this non-uniform shell that surrounds the hotspot. So think of this in the first part of the pulse, you burn off more later, and then you squeeze it a different way. And so then you end up with all these row R variations of the shell. So then we moved away from that for quite a bit, but we had to go back to get more efficient. And when we moved away, we went to low gas hohlraum, so significantly reduced the fill in the center of the hohlraum. And we observed that we only had about 2% light back scattering out, or less than that, out of the hohlraum. We didn't measure the huge SRS and SBS back scattered back out anymore. And then so we worked on trying to bring cross-beam energy transfer back in the presence of these low gas hohlraums that were more efficient. And when we first started, people thought that maybe it wouldn't work quite as well, or maybe we need to get the backscatter issue again, but we didn't have either. And actually, it worked really well. So that's the key here, is cross-beam energy transfer in the low gas hohlraums. And actually, we're very predictive, which is another thing super happy about. My life's much easier, at least in setting the early time swings part. And then the late piece we can sort of get with our setting models. Yep, Luca.
You mentioned that some experiments are used for cross-browse viewership as well. How are those experiments different from the ones that we get?
Yeah, that's a great question. So of course, we also use these experiments to test our models that support the stockpile stewardship program. But specifically on this experiment, we had an external package, Charles Humans, you might know him. So we worked with his team and they're looking at the survivability of materials under intense radiation neutron environments. And so they actually commissioned their diagnostic on this experiment. And then they'll be doing a series of experiments over the next year. So how well do our materials survive under these conditions?
More observation. So essentially, this is more of a control boosted nuclear bomb, right? Whereas in like it's a little more, you're not letting the reaction like just simply go. Because like for example, we were talking about the outlater, that is reminiscent to the tamper of the actual outside shell, like an implosion device.
Yeah, so one comment, this is not a thermonuclear test in the laboratory. And then another comment is the amount of fuel that's in these targets is so small, there's no chip. We want to burn all. We want to burn all. That'd be awesome. That'd be about 70 megajoules of energy. So it's not going to be. Yep.
Looking at the laser powered delivery, I noticed that in the action with the daughter, you have this kind of squiggle at the top like maximum laser power. What's the reason for that, or is that just because
See if I can find one.
you have a difference between this one again?
Yeah. That's just how all the laser can do. Yeah.
Let's thank our speaker again. Thank you for the best birthday gift I ever received. Our guests, they have to get lunch and go on the tours, so it's had spilling out further. So thank you.